Imagine opening GitHub to check Microsoft's official documentation, right?
Just a normal Tuesday morning.
Yeah, exactly. But you log on and you find 73 of their core repositories are just completely wiped out.
Wow.
No warning, just this stark message saying access was disabled due to a terms of service violation.
That is terrifying.
Right. You try to pull code for Azure samples, Microsoft Docs, and it's all gone. And the crazy thing is, that isn't some hypothetical disaster scenario. That actually just happened.
Yeah. And the fallout from an event like that, I mean, it's immediate. Development pipelines break. Automated builds just fail instantly.
Thousands of developers are suddenly blocked.
Exactly. But what makes this particular incident so concerning? It's not just the scale of the disruption. It's the fact that the attackers didn't even have to break into Microsoft's servers to do it.
Right. They didn't smash through a firewall.
No, they simply used the ecosystem's own mechanisms against it.
Well, welcome to today's deep dive. Consider this your daily high-impact cybersecurity briefing. We are basically bypassing the noise and looking straight at the mechanisms behind today's most critical threats.
And we've got some wild ones today.
We really do. We are tracking this very clear, very dangerous trend across recent security advisories. Threat actors are no longer trying to smash through the perimeter, you know. They are exploiting the inherent trust we place in our platforms, our open source packages, and our administrative systems.
Yeah, we are basically witnessing the death of the traditional perimeter.
Right.
I mean, when the tools you use to build software and the platforms you use to distribute it become the actual vehicles for the attack, you can no longer rely on just drawing a circle around your network and defending the edge.
Because the threat is already inside the house.
Exactly. And it's operating with legitimate credentials.
So let's look at exactly how they are getting inside, starting with that massive GitHub takedown. The core issue traces back to this self-replicating open-source supply chain worm called Miasma.
Right, Miasma.
And the sources indicate Miasma is a variant of an older worm, Mini-Shai-Hulud, which was created by a threat group called Team PCP. The sheer audacity of this worm is just wild.
It really is.
So back in May, this group compromised a highly popular PyPI package called Durable Task, right? It's widely used in Python. Then, a full month later, that exact same ecosystem, but not just Python. The ports for .NET, Go, Java, JavaScript, all completely taken down again.
Yeah, security researcher Paul McCarty made a really astute observation about that timeline.
Oh, yeah.
Yeah, he noted that when the epicenter of an attack in May becomes the epicenter of a massive multi-language takedown in June, you are looking at a persistent infection.
Ah, so they never really left.
Exactly. The initial response probably just focused on removing the malicious code that was published. But they failed to eradicate the underlying unauthorized access. So the attackers either kept the original stolen credentials or
Minted new ones.
Right. They used their initial access to quietly mint new persistent authentication tokens before anyone even noticed.
So it's, I guess it's kind of like a security system ignoring a burglar because they walk through the front door wearing a perfectly valid stolen employee badge.
That's a great way to put it.
So they essentially cut a spare key while they were inside the house the first time.
Yep.
But I want to understand the mechanics of the spread here, because if an attacker compromises a single Python package, how does that magically cascade into infecting .NET and Java libraries across 73 Microsoft repositories?
Well, that is the defining characteristic of a supply chain worm. It's designed to self-replicate.
Okay, how?
It harvests credentials from the machines of the developers who inadvertently install the compromised package.
Wait, just by installing it?
Yeah. When a developer runs a standard install command, the worm executes quietly in the background, and it aggressively scans the developer's local machine for any stored authentication tokens.
Looking for what, exactly?
Specifically looking for session tokens for package registries, things like NPM, PyPI, or Maven.
Wow, so it's turning the victim into the new attacker.
Precisely. Once it steals those tokens, the worm automatically authenticates to those registries using the victim's identity.
Unbelievable.
Then it checks to see what other packages that specific developer has the rights to publish. And then it injects its own malicious payload into those packages and pushes the new infected versions live.
So because the publish event comes from a legitimate, authenticated maintainer's account,
With a valid cryptographic signature, yeah.
the registry just accepts it without question.
Totally blindly. The security tools on the registry side are completely blind to it. To them, it just looks like a really busy developer pushing a lot of updates.
But wait, let's talk about the developer side of things for a second. If I'm installing an NPM package, Doesn't something have to trigger the malicious code to run? I mean, I know security scanners specifically look for automated scripts that run during installation to catch exactly this kind of behavior.
Yeah, you're referring to lifecycle scripts, things like pre-install or post-install commands that are defined in a project's package.json file. For years, attackers relied heavily on those scripts to run their payloads the moment a package was downloaded.
So the scanners should catch it, right?
Normally, yes. Modern security scanners are highly trained to flag suspicious activity inside those specific files. But the Miasma wave is using a technique identified by researchers at Endor Labs and Step Security. It's called Phantom JIP.
Phantom JIP. Okay, what exactly is a JIP file and how does this bypass the scanner?
So in the Node.js ecosystem, you sometimes need to use code written in C or C++ for performance reasons, right?
That makes sense.
To compile that native code during the installation process, developers use a build tool called NodeJIP. And the instructions for that build tool are stored in a tiny configuration file called binding.jip.
Okay.
It's a legitimate, deeply embedded part of the Node infrastructure.
Got it. So it's basically a blueprint for building software components. How are they weaponizing a blueprint?
Well, the binding.jip file is essentially this JSON-like text file that defines variables and commands for the compiler. The attackers figured out that they can actually embed shell commands within the variable expansion phase of this configuration file.
Oh, wow.
Yeah, they are taking a tiny 157-byte binding.jip file and hiding a command in it, a command that tells the system to reach out to the internet, download the Bun JavaScript runtime, and execute their credential harvester.
That is so sneaky. I think I understand the evasion now. It's like a malicious architect slipping an instruction to demolish a support beam, but they put it into the electrical wiring diagrams.
Yes.
And the building inspector is only looking at the structural blueprints, the pre-install scripts, so they just pass the inspection. They aren't looking closely at the electrical schematics for structural threats.
That is a perfect way to visualize it. The security tools see the .jip file and simply assume this system is preparing a routine C++ build step. They ignore it, completely allowing the hidden command to execute with the full privileges of the user running the install command.
And once that payload drops and they download that bun runtime you mentioned, the attack pivots.
It does.
So we've seen how they poison the distribution channels to get onto the machine. Now let's examine what they do once they actually have a foothold in the developer's local environment. The sources highlight this new piece of malware called Ironworm, right?
Right, Ironworm.
It's a Rust-based information stealer, and it's distributed through poisoned NPM packages by an account named Asteroid DAO.
And while the Miasma worm has this huge, wide net to replicate itself, Ironworm has a very specific, highly targeted shopping list.
Yeah, what's it looking for?
It is heavily focused on hunting down environment variables and secret files associated with AI coding assistants.
Really?
We are talking about API tokens for OpenAI Codex, Anthropic's Claude, Google Gemini, and tools like Cursor.
Why the heavy focus on AI tools, though? I mean, if you have access to a developer's machine, you could steal AWS keys or database passwords. Why prioritize a chatbot token?
Well, AI coding assistants require extraordinary levels of access to actually be useful. Think about it. To analyze your code base, suggest architectural changes, or debug an application, those AI tools need deep, unfettered access to your source code.
Oh, I see.
They need your version control history, and sometimes even your deployment environments. The tokens that power those tools are effectively master keys to the kingdom.
That makes total sense. And the sources mention a terrifying detail about how Ironworm uses this access. It actually mimics Anthropic's AI by introducing malicious commits under the author name Claude.
Yeah, it is a brilliant piece of social engineering via version control.
It really is.
If a security auditor or, a fellow developer is reviewing the commit history of a repository and sees a change authored by Claude, they're highly likely to assume it was an automated optimization or just a benign code generation step.
They are far less likely to scrutinize it line by line than a commit from some unknown user.
Exactly. Just blends right in.
But I have to push back on the stealth aspect here for a second. The report notes that Ironworm scrapes immense amounts of data and hides behind an eDPF kernel rootkit to mask its processes.
Right.
If this malware is actively scraping files and opening network connections, how is the endpoint detection and response software, the EDR, not just screaming at the Security Operations Center? I mean, doesn't a kernel rootkit essentially own the machine?
So eBPF, or Extended Berkeley Packet Filter, is this technology that allows programs to run in a sandboxed environment inside the operating system kernel.
Okay.
It was originally designed to safely trace system performance and monitor networks without actually modifying the kernel source code.
Sounds useful.
It's incredibly powerful. However, Ironworm abuses this power to fundamentally alter the reality the operating system perceives
Wait, altering reality how?
by hooking into system calls. So when your EDR software asks the operating system kernel to list all the running processes or active network connections, that request is a system call. The eDPF rootkit intercepts that specific call before the kernel can even respond. It dynamically scrubbed its own malicious process IDs and network sockets from the list.
You're kidding.
No, and then it hands the sanitized fake list back to the EDR. The security software remains totally silent because, according to the kernel itself, nothing malicious is happening.
Wow. So it's basically a corrupt court reporter altering the transcript before the judge even reads it.
Exactly.
Is there any defense against something operating at that deep of a level?
Fortunately, yes. The source material provides a really clear technical resolution for this. The process hiding tricks of the eBPF rootkit actually fail on Linux systems where kernel lockdown is enforced.
Kernel lockdown.
Yeah. Kernel lockdown is a security feature that restricts even the root user from modifying the kernel code or accessing kernel memory.
Okay, so it sets a hard boundary.
Right. When you enforce that boundary, the eBPF payload cannot effectively manipulate those system calls anymore. The illusion shatters, and the malicious processes suddenly become visible to the EDR tools again.
That is good to know, but obviously requires very strict environmental configuration.
It does.
But, there is another detail about Ironworm that I find even more concerning than the rootkit, and it's how it handles its command and control, its C2 infrastructure.
Oh, yeah. This part is wild.
Normally, malware has to communicate with an external server controlled by the attacker to receive instructions or exfiltrate data, right? And network defenders can usually spot that anomalous traffic going to some random IP address in Russia or wherever. Ironworm doesn't do that.
No, it doesn't. The researchers at JFrog found that Ironworm turns GitHub itself into an adaptive C2 server.
It's just crazy.
It uses the stolen credentials to manipulate GitHub Actions workflows across repositories.
I really want to understand the mechanics of this. How does a massive public platform like GitHub serve as a command center without triggering their own internal malware scanners?
So the malware actively searches the commit histories of repositories it already has access to. It's looking for specific, hard-coded strings. The example given in the report is the phrase fired laser.
Fired a laser.
Right. The attackers simply push a seemingly innocuous text update to a repository containing that trigger string.
So it's like a dead drop in a spy movie.
Exactly like a dead drop. The Ironworm agent running on the infected machine is constantly polling GitHub for that specific string. When it sees fired a laser, it knows a new payload or updated instruction set is waiting for it.
Wow.
It retrieves a new JavaScript file embedded in the repository, effectively updating itself dynamically.
And from a network defense perspective, this is an absolute nightmare. Your corporate firewall is just seeing standard TLS encrypted HTTPS traffic flowing to github.com.
Which is universally whitelisted in enterprise environments.
Right. You can't block it. Network level detection is completely neutralized here because your security appliances are implicitly configured to trust the traffic. The threat actors are hiding in plain sight on the safest domain on your network.
They are piggybacking entirely on legitimate infrastructure. Like you said, you cannot block GitHub without grinding your entire engineering department to a halt.
Which brings us to the final piece of the puzzle today. We've seen how they subvert the code distribution with worms like Miasma. We've seen how they subvert the developer's local environment and network traffic with Ironworm. Now, we arrive at the absolute backbone of the enterprise, right? The network infrastructure itself.
Yeah, this is where the threat model shifts from code repositories to physical and virtual routing appliances. We are looking at a critical situation with Cisco Catalyst SD-WAN Manager.
The facts on this one are just brutal. We are dealing with CVE 2026-2020-45, a high-severity flaw with a CVSS score of 7.8. It allows an attacker to execute arbitrary commands as a root user simply by uploading a crafted file to the system.
Nope.
I mean, command injection feels like such an archaic vulnerability, Yet here it is in a modern enterprise network manager. How does uploading a simple file lead to root access?
It really comes down to insufficient validation of user input. Standard stuff, but deadly. The SD-WAN Manager has a feature that allows administrators to upload .csv files.
Like spreadsheets.
Yeah, exactly. Perhaps for bulk importing configurations or device serial numbers. The backend software takes that file and processes it using a shell script.
Okay, I see where this is going.
Right. If the system fails to properly sanitize the name or the contents of that uploaded file before passing it to the shell, an attacker can embed terminal commands directly into the file parameters. The system executes the command under the assumption that it's just handling a benign data import.
But I was looking at the advisory, and there is a pretty significant caveat here. To pull off this command injection, the attacker must already possess netadmin privileges on the affected system.
That's right. It is an authenticated vulnerability.
So if they already have netadmin access, haven't they already won? Like, why do they need this new vulnerability to get root?
Well, netadmin is a highly privileged role, absolutely. But it is bounded by the application's logic. A netadmin can change routing tables, modify network policies, disrupt traffic, but they are still operating within the sandbox of the SD-WAN manager software. Root access, however, gives them control over the underlying Linux operating system itself. With root, they can install persistent backdoors that survive a software reset. They can modify system logs to erase their tracks and pivot deeper into the entire network architecture.
I see. So they need two keys to launch the missile, basically. They need root to guarantee they can never be kicked out. But that brings us to the most pressing question. How are they getting that netadmin password in the first place?
Well, they aren't guessing passwords. They are exploiting older, previously known flaws to bypass authentication entirely.
Oh, of course.
The advisory specifically points to threat groups, like UAT 8616, chaining this new flaw with older vulnerabilities. They are abusing CVE 2026-2182, which was a maximum 10.0 severity authentication bypass from earlier this year, or even CVE 2026-2127 from last year.
So let me get this straight. They used the 10-point flow flaw from May to trick the system into granting them netadmin access without ever knowing a credential. Then, once they are inside the application, they use this new 7.8 file upload flaw to break out of the application sandbox and take over the underlying operating system.
It is a textbook exploit chain.
It really is.
And understanding that chain is the key to actually defending against it. Threat actors rely on organizations patching slowly. They know that if they can find a single unpatched server with that older authentication bypass, they have a clear path to complete system compromise.
This leads us to the most critical, actionable advice for this entire briefing. If you are managing Cisco SD-WAN infrastructure, listen closely. There is currently no patch available for this new vulnerability.
None.
Let me repeat that. CVE 2026-2245 has no fix right now.
And, the absence of a patch for the 0-day sounds really alarming. But remember the mechanics of the chain we just discussed. If you break the first link, the entire exploit fails.
Right, so your immediate mitigation is to ensure your systems are upgraded with the patch Cisco released back on May 14th, 2026 for the older CVE 2026-2182 flaw. If the attacker cannot bypass authentication to get netadmin privileges, they cannot upload the crafted CSV file to trigger the 0-day command injection.
It perfectly illustrates why patch management must be comprehensive. You cannot just focus on the newest threats. You must close the foundational gaps. Furthermore, defenders should not just patch. They must actively hunt for indicators of compromise.
What should they be looking for?
Cisco advises administrators to investigate the /var/log/scripts.log file on the SD-WAN manager. You're looking for any suspicious .csv file uploads.
Okay.
The logs might show a script executing a path to a highly suspicious file, or even something attempting to blend in, like vsmart_serial_numbers_safe.csv. That log file will reveal if someone has already attempted the command injection.
Check your scripts.log for weird CSV activity and rigorously verify that the May 14th patch is actually deployed across your environment.
Do not wait on that.
Absolutely. Well, let's pull the threads of this briefing together. We are seeing a unified strategy from threat actors across vastly different domains today.
Yeah, the landscape is entirely defined by the subversion of trust.
Open source supply chains are being poisoned from the inside out. Worms like Miasma aren't breaking cryptographic locks. They are stealing the keys and using deeply embedded, unmonitored compilation files like binding.jip to infect systems silently.
And on the endpoint, the developer's local environment is under siege from malware like Ironworm. It specifically targets the highly privileged tokens of AI coding assistants to gain leverage over source code while utilizing eBPF kernel rootkits to gaslight the operating system's own security tools.
Gaslighting the OS, I love that. And on the enterprise backbone, advanced threat groups are chaining old authentication bypasses in Cisco SD-WAN to trigger a brand new, unpatched command injection flaw, elevating their access from application administrator to complete system root. Break the chain by patching the old to protect against the new.
Definitely. When you step back and look at the aggregate of these threats, it leaves us with a pretty profound problem to solve.
Well, so.
Today, we discuss attackers using GitHub as a literal command and control server, right? Dynamically updating their malware via commit histories entirely because our enterprise firewalls blindly trust that domain.
Right.
As malware continues to abandon external infrastructure and piggyback entirely on the legitimate whitelisted platforms we rely on daily, how long until our traditional concept of a safe domain becomes completely obsolete?
That is a chilling thought.
If the platforms we trust the most to build, deploy, and manage our software are the exact vehicles for the attacks, how do we architect systems that must assume everything, even the foundation itself, is already hostile?
We have to stop defending the perimeter and start defending the data itself. Thank you for joining us for today's deep dive briefing. Take these takeaways, audit those logs, verify your patch levels, and stay secure.